Hello again. You'll see we are going to continue our discussion of chemical nomenclature. In this video, we will begin with the introduction on naming ionic compounds. This video may be somewhat short, but it's the basics of naming binary ionic compounds. So let's go ahead and get started. Now, in the previous video we discussed about binary molecular compounds and how they can combine in different ways, and thus we have to deal with how we name them differently because we needed prefixes to help us understand the combinations. But in ionic compounds, we are always striving to make a neutral compound. If it's not neutral, it's still a charged molecule. So it would still be an anion or a cation. And so our compounds will always be neutral, and because of that fact, we have a reliable way of naming them and understanding why they are combined in such ways. The cation and the anion will be in such a way that the total number of positive charges from all the cationic units must equal the total number of negative charges for all the anionic units. If this isn't true, it's not an ionic compound. And we are going to represent this in the simplest whole number ratio of cations to anions, which we call the formula unit. You'll learn about how we predict these charges, but the common charge of sodium is +1. The carbon charge of chlorine as chloride is -1. If I have one positive and one negative, I only need one of each, and so we're going to have a ratio of 1 to 1. They cancel out. The common charge of potassium is +1. The common charge of oxygen is -2. And so if I have a -2, I need 2 units of +1 to cancel out. So I'd have 2 potassiums for every 1 oxygen. Aluminum is typically 3+. Chlorine is typically 1-. So I need 3 chlorines for every 1 aluminum to cancel them out. And the other very common situation is, well, iron is often 3+. Oxygen is 2-. How do we balance those out? The the least common factor, greatest common factor or least common multiple, whatever the one is, between those two, least common multiple, I think, is 6. So the lowest way we can do that is having 6 positive and 6 negative, which means 2 plus 3s and 3 minus 2s. They cancel out. One really cheap, cheesy way to do this is just take the number from the top of one and flip it down to the bottom of the other. But we must always, always simplify, because if I have a +2 and a +2, it's not 2 and 2, it's 1 and 1. It's always the simplest ratio. Now, how do we predict the charge? So the idea is, taken from our last chapter, all elements strive to achieve a noble gas-like electron configuration. They either want to completely fill up their p orbital or completely empty out their s orbital, or s&p orbital in the case of aluminum. They are going to try to get to the next closest noble gas. They're always going to go one way or another to try to achieve that. That is the most common case. So in our basic elements 1A through 7A, you can simply count the number of spaces that would have to move to the left or the right. Remember, losing electrons makes you more positive. So group 1A would move one to the left. It would have to lose one electron to make it positive 1, to make it like a noble gas. Group 2A would have to move 2 to the left, moving essentially beryllium would move boom, boom, and that puts us at helium over here. If we're moving to the right, we are gaining electrons. Gaining electrons makes us negative. Oxygen gains 2 to become like neon. Fluorine gains 1 to become like neon. Nitrogen gains 3 to become like neon. That we can use the fact of where they're at, that +3 or -3 depends on how many electrons we need to add or subtract. Now, transition metals are a little bit trickier because of the mixture of the 4s and 5s orbitals and the 3d or 4d orbitals. We can lose electrons from the s, but we can also lose electrons from the d. Because of that, we often have more than one possible charge. And because of this, we are going to need to think about the context of what it is to figure out what is the charge. You'll notice iron could be +2 or +3. Chromium can be +2, +3. Nickel could be 2, 3, or 4. Copper 1 and 2. Palladium 2 and 4. Platinum 2 and 4. Gold 1 and 3. Mercury can technically be 1 or 2. There's only 3 elements that are only one possible charge in the transition metals. That is zinc and cadmium and silver. Zinc, cadmium, and silver are so often +1 or +2 that we will always assume they are their expected charges. That is because of the magic of the filled orbitals. That zinc has a completely filled 3d orbital, 3d10, and so it is very easy to lose its 2s electrons. It's the 2 electrons in the 4s, but it's almost impossible to lose any of its completely full 3d. Silver is one of those exceptions. It is 5s1 4d10, and so it only wants to lose 1 electron from its s. Cadmium is like zinc. It wants to lose 2 electrons from the s. And so they tend to act like that. Now, how do we do this? How are we going to name these guys? Pretty straightforward. When you're dealing with the cation, there are 2 possibilities. Possibility 1, if there is only one stable charge, which we call the oxidation state. If there's only one stable charge possible for that element, then there's no reference to the charge at all. We don't need to refer to the charge. We know this is what it is based on where it is on the periodic table. So this is always true of groups 1A, 2A, 3A, and those 3 special transition metals, zinc, cadmium, and silver. We don't have to say it's zinc 2+. We will assume it's zinc 2+. If it's barium, which is in group 2A, we know it's barium 2+ because it's in 2A. If I say aluminum, we know it's aluminum 3+ because it's in 3A. So we do not need to reference that. Now, if it has more than one stable oxidation states, which is most of the transition metals, we will reference the charge of the metal. Note, this is not the subscript of the metal. It is the charge of the metal, and we will give it as a Roman numeral, which is just a verbal cue. Iron II, we call iron 2, but it's the Roman numeral II for 2. Iron 3 would be iron III, but we just call it iron 3. There's, I think the highest charge we will maybe see is 5, but 4 is probably more common, which would be IV. Remember, V is 5, and when we put the I before the V, it means 1 less than 5. Now, because these are always neutral compounds, we will not have to reference the charge of the anion. We will just give the anion the IDE suffix. We don't need to reference the quantity because the positives and negatives must always cancel out. Now, if there's not an obvious reference to the transition metal, we need to look to the anion to help us figure it out, as we'll see in the next couple slides. So I'm going to go to my document camera and we'll work through these problems, both this slide and the next slide, and that's where we will stop, going from one way to the other. But okay, I'm going to pull up my handy dandy tiny little mint tin of periodic tables. You'll have to trust me because it's not the most unfocused. So we'll start with a hard one. Iron. Iron is a transition metal right there. More than one possible state. Oxygen is right here, 2 away from neon. So when I go to name this guy is -2. How we would go about going this, we can often flip these over. So we can often use this as a hint. If this matches this, then this will match this. So with that in mind, we don't need to say there's 3 oxygens. We just say oxide, regardless of charge. This guy Fe is iron, but because it's a transition metal, we have to reference its charge. This is iron 3 oxide. We put the 3 in parentheses. Now we have Pb, which is down here, transition metal that's kind of outside the unit, and S, which is sulfur. Sulfur is in group 6A, right below oxygen. So sulfur is -2. Now, one of these, this does not match. 1 and 2 do not match. So what's the likelihood of this matching there? Oh, well, that has to be +2 in order for that to match. So this is sulfide, but this is, Pb is lead. So lead 2 sulfide. And that 2 plus, we have Al, which is in group 3A. Pretty straightforward. Cl, which is right here, 7A. So that is just, we don't even need to know the charge. We can just say aluminum, or if you're British or European, it's aluminium. But if you're American, it's aluminum chloride. Chloride. Ca is right here. So F is right here. We don't need to reference this. So it's just calcium fluoride. We don't need to reference how many numbers because it's understood. Even though this 2 plus, 1 minus We don't need a reference. Mn. Mn is right here, right in the middle. So, ooh, that's a little tough. Oxygen is right here. So, with that in mind, oxygen is -2. These do not match. 1 and 2 do not match. So, this is 2 becomes 4. I'd have to double the 1 to get to 2. So, I double the 2 to get to 4. So, this is still oxide. But this is manganese, not magnesium, but manganese 4 oxide. Manganese 4 oxide. Now we have zinc. One of our weird exceptions right there. Zinc and Br right there. So it just becomes zinc bromide. It's always the same thing. Silver and chlorine. So it becomes silver chloride. We don't have to say silver 1. It is assumed it's silver 1. But back to iron. Well, this is different from the starting guy. This is 1, 1. Oxygen is -2. You'll notice that 1 and 2 don't match. So this would also have to be doubled. 2 minus and 2 plus. So it's still oxide, but this guy is iron 2 oxide. We got 2 because it's a 2 plus charge, not because there's 2 of them there. Iron 2 oxide. That's how we would go about naming these guys. How would we go from name to structure? Let's see, get this readjust. This is where it can be a little bit easier or harder depending on how you understand the periodic table. So strontium, we start with strontium right there, group 2. Chlorine right there, group 7. So first thing I would start is I need the charge of each guy. Group 2 means that's 2 plus. Group 7 means we move 1 to the right, so it's -1. I'm going to cross these down and simplify. So SR1Cl2. So SrCl2 is our structure. Potassium, that's K. Nitride, it's N. Let's look at our charge. Potassium is right there, +1. Nitrogen is right there, group 5, so it has to move 1, 2, 3, -3. So flopping them down, K3N. K3N is potassium nitride because that counterbalances these. Cobalt to fluoride. Well, cobalt is CO. Cobalt is a transition metal, but it tells us it is 2 plus. Fluoride is right here on group 7, so that's 1 minus. Crossing them down, COF2. Copper 1 oxide. Again, transition metal, but it told us it was +1. Oxygen right here moves 1, 2 over. Crossing it down, you have Cu2O. Rubidium, Rb, group 1, +1. Iodine, group 7, -1. So RBI. Rubidium iodide. And CD. This is probably the hardest one. CD. Cadmium. CD. And then chlorine is Cl. Chlorine is -1. Cadmium is like, oh God, it's one of the weird ones. We do have to learn. Zinc, cadmium are both 2+. Silver is +1. Essentially, we're putting these guys right here in these blanks. So zinc has to move 2 over. Cadmium has to move 2 over. Silver has to move 1 over. So cadmium is 2+. So CdCl2. That's probably the hardest one there. But if you can do that, you're well on your way. I'll see you for another video.